So, good evening, everyone. I am Chanda Devnath. Right now, I am pursuing my PhD from ISER Berhampur. So, I have selected for the PMRF fellowship this year. So, right now, I am a TA for this course, Reactive Intermediate and Carbene and Nitrene. So, the course instructor, Professor Rajeshri Samante, has taught you all lots of things till now. So today I will just try to explain some more problems based on this concept. So that will help you. That may help you in your to complete your course or to attempt some questions from assignments and future also. So let's start reactivity. So today we will discuss about some of the reaction of carbenes. So carbenes can undergo variety kind of reaction. One is insertion, second is addition to the multiple bond, third is skeletal rearrangement. I have shown one of the examples here. I will discuss this example after also. So first start with the insertion into CH, NH and OH bonds. So first let's start with the insertion into the CH bond first. So here I have shown an example where this type of diazocarbonyl compound is here, where which undergoes N2 elimination, like N2 will eliminate by the reaction of rhodium 2 catalyst. So N2 will eliminate and it will generate a carbene system. This carbene system can insert into this CH bond, like this one. This CH bond, it will insert into this CH bond and resulting a cyclopentanone ring. So most interestingly, you can see that after the ring formation, these two adjacent groups are anti to each other. So why? Because of this bulk, to reduce the bulkiness, when it will insert into this CH bond, it will get an arrangement where these two groups can be in anti to each other. So here, so in the first step, what is happening? Carbene generation is happening by N2 elimination by the action of rhodium catalyst, and when after this carbene generation, it will insert into the CH bond. So now next, for the next problem is similar to this one. So in this one, again similarly, then after N2 elimination, a carbene will generate and it will insert into this CH1 leading to this compound. You can see leading to this compound. And this is an important product because it can be used for the synthesis of toxin, mascarin. So it can be used. So it is an important thing to important compound to generate. So So that tolerance of various groups. So here there is a compound which is CH2N2, and when the carbene is adding to this compound, the cyclopropane ring kind of will form here, the similar kind of reaction. And here when there is a ester group, it will be totally unreacted. That like not like that it will attack here and it will open the ring. No, nothing will happen. It will just generate a carbene and it will be added to this double bond, giving us the cyclopropane kind of ring, the fused ring, 96%. So here there is, I have shown a problem. I have given a reaction. So anyone of you can see that what will be the product? Anyone of you can think about the product? As I am talking about carbene, so it will obviously go through carbene. It's a common sense. So, but anyone of you can think about the product? What will be the product? So this one, I already have given our task for this week. So this is also a task for this week. Just think. There's no marks on this. This is just to reconnect with the lecture or the session I am going through. Just next week, so that you can reconnect what was been told or what was taught last week. So just think about this reaction. What can be the product? So I will explain this reaction next week. So think about this reaction. This one. Obviously it will go through a carbene intermediate. So you don't have to think about that on. So think once. So let's come to the next one. That is another uh, importance of this reaction. That is chemoselectivity of zinc carbonate. Chemoselectivity, zinc carbonates are electrophilic. Chemoselectively, the zinc carbonates are electrophilic and react chemoselectively with the more nucleophilic double bond in dienes or polyenes. Polyenes means when some compound containing more than 3 or 4 double bond. It is called polyene. Mostly 4 double bond. 4 double bond is called tetraene or something, but more than that it will call polyene. And diene we know like 2 double bond. So it will select chemoselectively. Chemoselective words means chemically selectivity is there. Stereoselective means stereo selection is there. So that's why we're talking about stereospecific and stereoselective. That is the selectivity is generating because of the stereochemistry. Because of the stereochemistry, that one is cis, one is trans, and because of the stereochemistry. But chemoselectivity means that the selectivity arises due to the chemical property, of the reactive center. So here, as you know, from the Simon-Smith reaction, it will generate a carbene, that is it will generate a CH2 carbene, it will generate a CH2 carbene. So it will generate a CH2 carbene. So now the question is, there are 2 double bonds. One is here, one is here. So why it will add? There are 2 double bonds. So there will be a selectivity because that is not like if there because both the double bond are not same in nature, both are different. So there will be a selectivity. So why it will get attacked? So as I told, this reagent is electrophilic. This reagent is electrophilic. Why? Because this is a electron deficiency is here. I have told in the first slide that is a neutral electrophilic compound. So it is electrophilic. Like there is an electron deficiency is here. See, you can see there is a six pair of electron. Sorry, 3 pairs of electron. Total 6 electron. So there is already a electron deficiency. So obviously it will not react with the electron deficient something. So here this double bond is electron deficient. Why electron deficient? Why this is electron deficient? Why? Because there is an electron withdrawing group. This is the ester group. You may have heard about the Michael reaction or Michael acceptor or something. This type of compound is called Michael acceptor. Type of compound are called Michael acceptor. So due to the resonance, due to this resonance, due to this resonance, there is a possibility, there is a partial delta positive charge is getting generated due to this resonance. Partial delta positive charge is generated. So that's why this double bond is less electron rich. There is electron deficiency, but here no such electron withdrawing group is there. More important, there are two alkyl groups, so it will show some plus I effect. We all know that all the alkyl groups have some plus I. You have learned in your plus 2 or graduation or somewhere that all have plus I effect. So this type of this due to this plus I effect or inductive effect. Due to this inductive effect, this double bond is comparatively electron rich. So that's why this carbene will selectively react with this double bond and giving us cyclopropane ring here, not here. Understood everyone that because to choose that because it is electron efficient. The next problem is the chain directing effect of hydroxyl and ether functions. So when there is a part, the particularly interesting aspect of this Siemens-Smith reaction is that the stereoelectronic control exhibited by the proximal OH or OR group. So here you can see there is a OR group above the plane. This is the above the plane. There is a OR group. So it will favor through a coordination with the zinc compound. The oxygen will coordinate with the zinc compound because zinc has a zinc. It will there is a zinc plus 2 system, so it will have some vacancy to to coordinate with the lone pair of the oxygen, and and due to this coordination this type of product will form selectively above the plane because this OR group is above the plane. So this type of coordination favors the cyclopropanation to occur from the same phase of the double bond as the oxysubstituent. What does that mean? That the oxysubstituent, if the oxysubstituent is the below the plane, then the double bond would be then the cyclopropan ring would form below the ring, below the plane. But if it is as above the plane, so the cyclopropan ring has been formed above the plane. Simple. Like whenever like if this group is above, this cyclopropan ring will be above, but it should be adjacent, not like too far. It should be adjacent to control because for coordinating also that OR and that oxygen and zinc should be close enough. If the distance is too much, it can't coordinate. No? It can't come in contact to coordinate with the zinc. So the distance can't be too much. So this OH group should be quite close to the double bond so that this coordination can happen. So here I have shown an example where this carbene is getting generated here in the similar way, Siemens-Smith way, and see there is a OH group and there is a alkyl group. So it will give a steric effect, it will give a coordination effect. So why this cyclopropan ring will form? And here is also a methyl group. It will also give a steric effect. This is closer than this one carbon distance. This will give a steric effect, this will give a coordination effect. So the coordination effect is so predominant that the steric of this small methyl group, this is a methyl group. When nothing is written, that means it's a methyl group. So the coordination is so much important that we can eliminate the steric effect imposed by this methyl group. So that's why it will selectively give a product above the ring. See? Just above the ring because of this type of coordination this zinc compound, zinc carbenoid compound will come approach from the above plane because of here coordinate, and it will approach from the above plane and giving us this compound in a major amount like 81%, almost a high yield. So this the following order of decreasing directive effect has been observed in a way that if there is a OH, then the coordination will be highest. If OR, then it will be lesser than that one, less than that one, and if it's carbon, it will be less than least. So like if some compound, I haven't seen such compound yet. If I would see such type of compound, I will add that in the next session. That if it is in a compound where there is a OH group, OR group, and carbon, or any two of these three, so we will consider the coordination of OH group rather than the OR, because the coordination effect of OH is higher than the OR. So if there is a OH and OR in the same like one will be both are in a same distance, OH and OR both are in the same distance, then we will consider the coordination of the OH group, because the coordination effect of the OH group is higher than that of the OR. If I could see such type of problem, then I will add up that next session so that it may help you to understand more about this line I have written here. It will help you to learn more about this line. So the next is Furukawa's reagent, which is a modified Simon-Smith reagent. Here, iodomethyl zinc, iodomethyl zinc has been used. Like why we are that in that one what we are using, that we are using something zinc iodide or something. So here we are using iodomethyl zinc derived from the diethyl zinc and diiodomethane. Like that was what. So, or its modification using chlorodiamethane instead of diiodomethane. So this type of thing, this reagent, this Furukawa's reagent, when we use iodomethyl zinc or something, we may use the flexibility of the choice of solvent it increases, because in that one we are using diethyl ether. Most of the cases we are using solvent as a diethyl ether, and we all know diethyl ether containing an oxygen atom, and when there is oxygen atom, it has some coordinating property. It will coordinate somewhere, like if there is any coordination property is there, so the solvent will coordinate here. So if there is a functional group also here, so it may take part into that reaction or something. Solvent may hamper the reaction. So the advantage of this Furukawa's reagent was that after using this reagent, the reagent was homogeneous. Like the homogeneous, the reactivity will be high, obviously, that because it was homogeneous with the normal organic compound. And the second point is, in case of this reagent, we can use less coordinating solvent like DCM, DCE, that is 1,2 dichloroethane, that is DCE, dichloromethane, DCM. We can use all these because these are highly non-polar and highly non-coordinating. So these won't affect the other substituents of the reaction. So and also it won't coordinate with the zinc also. Like we just want to coordinate if there is any functional group is here in the substrate, that can coordinate the zinc to help the reaction or something. But if the solvent coordinate with the zinc, it will decrease the reaction, because if the zinc is getting trapped by the solvent, it can't react with the substrate, so the reactivity will decrease. So that's why when we are using some non-coordinating solvent, the zinc carbonate will be more free to react with the substrate, so the reactivity will increase. So that's why this is the advantage of this reaction, that when we are using some, we can get a product in a higher amount, in a higher yield. So here I have shown two examples, simple example, where when this cyclohexene ring react with this compound and giving us this type of compound, and in a double bond alkene system, which will give us this type of keeping. And see the stereo selectivity. This is how stereo specificity is there. Like the alene, the alene geometry is restored here. The H and CH3 are in a same place. So it is restored alene geometry. So what you can see that is what from the product, from the, like, if we don't know, like, somehow in a reaction we have done a reaction, we have generated a carbene, for like we know that it is a carbene, but how can we know that it is a singlet carbene or a triplet carbene? So we, in a chemical way, in a spectroscopic way, we can do something like one will be from ESR active, one will be ESR non-active or something else. But in a normal chemical way, we can also determine it is singlet or triplet. If the carbene, if we will just react the carbene with a simple alkene, if we are getting stereospecific product, then that is singlet carbene. If we are getting stereoselect, like mixture of two products, it is triplet. So here we are getting a single product, so it is a to generate a singlet carbene. So the next is skeletal rearrangement. So here we can see that the addition of the carbene to an aromatic ring leads to a ring expansion. How is possible? See, we know that if there is a double bond, there will be formation of a cyclopropane ring. So in a benzene ring, there are three double bonds are there. So when you see, the benzene ring is so stable because it's aromatic. So, and it that Huckel's all satisfy all the Huckel's rules. It is aromatic. It's too stable. But this reagent, this carbene, is so reactive. It's too hard to react with benzene sometimes. Like, it's too hard. Like, we will to react, to work with a simple benzene is quite hard, because benzene is so stable and so unreactive. So it don't want to react. It doesn't want to react with anyone because it's so stable. But this reagent is so reactive that it will break the aromaticity. It will break the aromaticity almost. So it will react with the double bond, one of the double bond, and giving us this compound. So we can see this compound is not that much stable, because there is a 6-member ring with a fused 3-member ring. So it's not that much stable. So it will be an equilibrium with this type of compound. What is happening here? See, this is cyclopropanation is happening with, in the like previous way, like the double bond cyclopropanation. There is a skeletal rearrangement is happening, while the double bond is getting shifted and giving us this cycloheptatine kind of moiety. So there is equilibrium between this and this. So the position of the equilibrium is depends on the substituent of the carbene. Like, what are the carbene here after the carbene generation, or after the after this N2 elimination, after this N2 elimination, what will be the carbene? The carbene will be this one, Cn, sorry, Cn and Cn. So this will be the carbene. This will be our carbene. And here what will be the carbene? This will be the carbene. After this N2 elimination. So this will be our carbene here. This will be our carbene here. So here see the carbene substituted as Cn. These are 2 electron withdrawing. It has minus I plus minus R, that is resonance effect, minus R. It is minus. So this one is highly electron deficient. This one it will react and it will give us this compound. This will be stable. This will be stable because of this. This will be stable. But here this carbene is not that much electron, because only one electron withdrawing substituent is here. So here this in the product will not be stable here. The reaction will not stop here. After this time the previous slide we have shown that rearrangement will happen and giving us this type of cycloheptatide kind of ring. So it depending on the substituent, we can get different product. In case of like with the equilibrium will shift by depending on the, let's see the one both of the cases the reaction is happening in the benzene, but just by differing the type of the carbene, we will get different product. So now I will discuss some previous year's problem. So I have some more time also. So I will discuss some previous year's problem so that it will give an idea that this whatever I will teach, whatever I will show after this, the previous year's all will be based on whatever I taught today. So, and this will also help to solve your assignments and or get some more idea about this course. So I will try to. I couldn't cover all the questions today. From after like it is a 4 week, so for the next 3 weeks I will try to complete all the previous year's questions based on this topic. So here is the question. So this is the question. While this is said that a reagent A required and the major product B is formed in the following reaction sequence. What will be the reagent A and what will be the B? So these are the options you can see. A is one is CH2Br2, B CH2Br2 again. So it will give what type of carbon it will give? As we know from alpha elimination, one CH will first one CH will be eliminated, then another CH will eliminate. So it will give this type of carbon. It will give after alpha elimination, after minus after alpha like after deprotonation we'll get this one Ag remove, and after alpha elimination we'll get this carbon CH Br. There's one bromine will eliminate, one bromine will eliminate CH Br. So as we can see this cyclopropane here two bromine atoms are here. So obviously this can't be the carbon. This can't be the carbon because there are two bromine. So it is so this can't be the carbon. Similarly, this one is same. So these two are first we can cancel these two very fast because in both of them the carbon will be this one. So if it reacts, what would be the product? Sorry. So if it would react, we would get this product. We would get it react, we should get this type of. Sorry, I don't have pen yet. As soon as I get a pen, so that it won't be a problem anymore. So it would be a should be this. It should be this. If this carbon would here, but here there are two bromine atoms here. So the option will be from these two. So now A option is the A we got this. A we got. Now the problem is with B. So after this formation of this one, so what will happen? This Ag will give Ag plus, and you may have learned the silver atom has a high what I say high probability, or I don't know, I can't remember the word, high probability to react with the bromine. If there is any halogen atom, silver atom, and we are getting silver ion or some silver cation, it will select, it will react with the halogen atom very fast. So what will happen? It will come here, then sorry, and so it is Ag plus. So Br will remove as a Br minus. So it will remove. It will get removed by R minus as a Br, and it will form AgBr. And the meanwhile, what it will generate? There will be carbocation will be generated. There is a carbocation. I can show you the. So this is the answer. So after this AgBr will eliminate and it will form AgBr. So here a carbocation will generate. You can see. So to stabilize the carbocation, as we know that triple bond, as we know that cyclopropene are very unstable. So to stabilize this one, this bond will break to stabilize this one, and we will get and also the favorable, because this breaking is favorable because we are getting a 6-member ring, that is also a stable ring. So this bond will, and will get a 6-member ring, and after that, that in medium there is a weight, water is there, so water will attack here and we will get this. So what will be the option? C. Option C is the right one. Okay, everyone understood? So you can take a note. I am giving 1 minute. So you can write all these things. So this is the solution. I have also written the solution properly. If anyone has any doubt also for for last 10-15 minutes, I will take those doubts if anyone has any doubts regarding anything. So let's go come to the next problem. It was given in GATE 2008. You have you know about the GATE exam. So here is the problem. So after it is a photochemical reaction. They just irradiate this one, like photochemical is irradiated this one, and it will give a intermediate I, and that will also give a product. So these are the options. So first, what will be the intermediate? Carbene, radical or carbene? What will be the intermediate? And what will be the product? So just take 1 minute and think once. Just take 1 minute. So this is the answer. Where this N2 is getting eliminated by the radiation photochemically, so it is getting energy because already there is a negative charge, and when it gets removed, we'll get a carbon, and this will as and there is a oh sorry and there is already a double bond is there, so it will attack some, and this is a single bond, so there will be ring inverse, like a ring rotation, and it will add into this adjacent double bond and giving us this 1,2 cycle addition. With Professor Rajeshi has already taught you, I have seen that. So it will add into this double bond, giving us this product. So which will be the option? This one. Everyone understood? So how this can be formed? This one. Here they just couple this one, like one of this one, or like two equivalent of this one just coupled. So we all know that coupling in carbene is not that much reported here. Coupling reaction on carbene. In radical is there is something in coupling reaction, but carbene there is no such kind of coupling reaction like this type of just two compound will couple. So this is the main. So what is cis butene? I will show. So cis butene, there four carbon should be there. So I am writing like this: one, two, three, four. Cis. So that's why I kept. So this is cis. So that's why I kept two position like this. So there is a two position. There is a. It will be one. This will be two. This will be three. And this will be four. I have written this like this because it's cis, so that I don't have to remove this one again. So there is a two position. There is a double bond. Two position there is a double bond, and 1 4 diol 1 and 4 there is two OH. So here there is a OH, there is also a OH. This is our substrate of this reaction. That is, so this is our substrate of this reaction. So first, when what will happen? This is a again the Simmons-Smith reagent. So it will add to this double bond. So we all know this Simmons-Smith reagent, and this is a it will this is a singlet one. So this is a singlet one. So it will add from a same position, like in a only one position. So there will, if it is as it is jade, cis means it as it is jade kind of system. So it will give only one compound, like no flipping, no hydrogen. Both the hydrogen will be same position. So this is our. I will remove this so that you can see. So this is the structure what I have written already. So after this carbene, there is a cyclopropane ring will form. The cyclopropane ring will form like this. So as I said that it will be in from the same position. See, both the hydrogen in the same plane, because there is a no chance of ring flipping. Sorry, bond flipping. So that's why both the hydrogen will be in the same position. So here this type of cyclopropane ring will form. So the first reagent work is done. The first reagent work is done. The second reagent, what is this? PCC-CH2Cl2. You all know about this reagent maybe. This is a Jones reagent, oxidation reagent. We all use this reagent for oxidation usually. Normally, it's not that much. It's easily accessible, so we can use, and it's not that much harmful. Also, we can use this. Not that much harmful, dangerous or something. So we can use this reagent. This is called Jones reagent. This is called Jones reagent. Jones. It's called Jones reagent. So what it does, it goes the oxidation of the OH. As they have written that one PCC, they have not written excess or something. So first one molecule of OH will be oxidized. One molecule of OH first will be oxidized. They have they don't have excess, they have added excess, they don't have written one equivalent, that means we can consider it as an excess. But first what will happen, one molecule of OH will be oxidized to the aldehyde, like this one. As there is a OH group adjacent to the C, and it can form a 5' ring also. So how easily this OH will react here and will form this type of moiety. This type of moiety will get this type of moiety. And PCC, this substrate, the product is still in PCC in the reaction mixer. I don't know you guys have you have gone through in labs or somewhere. You have said reaction, or you have seen how the reaction works in a reaction vessel. Already this has been formed. This has been formed, but PCC is not removed yet. PCC is still there. Some unreacted PCC will be still there. So what will happen in the reaction mixer? It will be oxidized to this compound because PCC is still there. So OH will be not as a kept as a OH, it will give this carbonyl compound. And formation of carbonyl compound is always favorable because it is strong bond forms. So that's the carbonyl compound formation is always favorable. So you that because the reaction is the, if you stop the reaction even the PCC is still there. So that's why this type of oxidation will happen. So what will be the product? So option A. Option A is our product. Everyone understood? So the everything is simple. The main thing we have to do the what is the structure. You have to draw the structure from the name. So you have to don't have to forget. You should not forget your basics like what is how to draw a structure from the name. So the next problem is this one. In the following reaction, the reagent A and the major product B. What will be the reagent A? So that this product will form. What will be the reagent A? So that it will form this product. And after this, everyone knows this reaction. This is hydrogenation reaction to cleave any bond or something. That it will give B. So think. I'll give it 5 seconds. Just 5 seconds. So let's just explain. So here if we have to as I don't know anyone of you known about this reagent or not. Anyone has know about this reagent? What is its work? No. So this is called Korechekos. I don't. It's a bit difficult to spell. Korechakos something. Sorry, I have written that in afterwards also. So this is called this Koresh reagent. So for what happens? So this type of reagent, when this type of sulfoxide, this is the sulfur and oxygen is there. This is called sulfoxonium. This is called sulfoxonium. When this type of sulfoxonium reagent we use, if there is an alpha beta unsaturated double bond, it will form cyclopropane. What I have just told, if there is this is called sulfoxonium. This is called sul sulfoxonium. This is sulfoxonium. Elite. Why elite? We know what is called elite. If positive and negative charge are adjacent, that is called elite. Here, there is a negative charge can be easily generated because the hydrogen is highly acidic. So when you add this with base, the 9H is a base, it will generate this type of carbon, this type of intermediate elite. So when this type of elite we use on this type of substrate, alpha beta unsaturated compound, alpha beta unsaturated like the Michael ester or any alcohol or anything, ester or alcohol, sorry, ester or ketone, carbonyl or anything. If there is this type of compound, if we use this reagent, it will give this as a product. Keep this as a product. I don't know you guys know about this one or not, or if not, you may learn about this afterwards. So this is called sulfoxylamide. When it added to a sulfur beta unsaturated double bond, it will give cyclopropane ring. But the main criteria is the cyclopropane ring has to be alpha beta unsaturated, like the electron withdrawing double bond. So with the electron donating double bond, that is electron, see here, there is no alpha beta unsaturated compound, like no electron withdrawing compound. So this is electron rich. This is electron rich. This is electron rich double bond. So these reagents are eliminated because if this won't react, this won't react, this won't react. So these two options are here. So what will be the reagent among these two? So then cyclopropane ring will form. How do you know this reagent? This diazocarbonyl compound. It will give a carbene here, this type of, and it will add to this position and give this product. So among the A is sorted. So now why this cleaving will happen? This carbon is due to hydrogenation, as the triple bond ring is too unstable. Usually it hydrogenates the double bond, but as the triple bond is too triple bond I'm saying sorry. As the cyclopropane ring is too much unstable, it will break the cyclopropane ring. So you can see now why will be the cleaving here, here, or here? Why will be the cleaving? That is the question. So the thing is, in case of you may have learned or you will learn or somehow. In case of hydrogenation reaction, the reaction is happening on the charcoal, the palladium charcoal. Reaction happening on the palladium charcoal. How the reaction happens? This substrate this substrate is getting absorbed on the palladium charcoal plate, like on the surface, palladium charcoal surface. Then this hydrogenation will happen. So the thing is, this get absorbed from the less bulky position, less bulky ring position. So see, for this ring, how many substituents are there? One, two, for this one, for this. For this bond, how many substituents are there? 1, 2, 3. So how many substituents are there? 3. For this one, how many substituents are there? Similarly, 3. But for this one, how many substituents are there? Only 2. Only 2. So this carbon-carbon bond is less sterically hindered to get absorbed on the palladium charcoal surface. So as it is getting absorbed on the palladium surface, so this carbon-carbon bond will be keep. So similar. So what will be the product? This one. What will be the product? This one. This bond will flip. This bond will flip. So this is the mechanism. See, this carbene will generate, and it will be added to the double bond, and this bond will flip as I said. Understood, everyone? So my name is I am almost to the ending. So the major product, what will be the major product for this reaction? What will be the major product for this reaction? So these are the options. Think once late December 2014 it was given. Just think once what will be the product. So let's start. So here you can see there is a we're adding this type of, it is called trifluoroacetic acid. This is called trifluoroacetic acid. When we are after this, it will remove the N2. The removal of the N2 will happen. And here a carbene center will generate. Here a carbene center will generate. As you know, carbene centers are electrophilic. Carbene centers are electrophilic. So it can add, or anything can add to the carbene center. So here, as there is a aromatic ring is here. See here, there is a aromatic. So there is a high excess density of electron here. Electron density is too much high. In case of aromatic ring or something, there is a there is a electron cloud here and above and below the ring. So there is a high electron density. So what will happen? So like the 3F3, this will just move from here and till that, and we'll get the product. I can show you the mechanism. See this one. So they haven't shown the carbene formation. They just assisted the reaction. If you form the carbene also, that is also okay. If you they just assisted like this, assisted they just. So what is happening? This carbene will generate here, and this electrophilic addition will be, sorry, nucleophilic addition from the benzene will happen and will give us this compound where, and as it is OMe plus, now this hydrolysis, then it will attack if OH is there, then what will happen? OH, OH minus, OH minus will attack, sorry, OH minus will attack the methyl, and this bond will be methyl oxygen bond, and the oxygen get neutralized. Oxygen get neutralized. So this is the product. So what is happening? One can think that a CH activation can happen here, but that is also a probability that CH activation may happen. But still, what is happening here? Here, a electrophilic addition is happening. Sorry, the nucleophilic addition is happening to the carbene center to the aromatic ring. So this is the product. So from the option, which will be the product, this one. This one is our product. Okay. So this is our almost the last, second last maybe. So the reagent A and B is in the following reaction are. So we have to predict the reagent. See, from the same substrate, there are two types of double bond. Where this is electron deficient double bond, as it is electron deficient because resonance is here. So this is electron deficient double bond, and this is only alkyl group is here. So it is comparatively electron rich. Comparatively electron rich. Comparatively electron rich. So here, by addition of this A reagent, we are getting this double bond to react. By addition of B, we are getting this double bond to react. So these are the reagents. So you can think once. In the previous one, I have already taught about the sulfoxonium halide. So here is also this given sulfoxonium halide. So you guys can see sulfoxonium halide. You can see sulfur and oxygen is there. If we open the write the reagent like this, so this is sulfoxonium halide. This is also here, and this is called sulfonium halide because see there is no oxygen. So this is called sulfonium. What will be the structure? The structure will be like this. Structure will be like this. It's called sulfonium halide. So one is sulfoxonium, another is sulfonium. So let's see. So here you can see this double bond is electron deficient, and I have already taught that by sulfoxonium halide this type of double bond reacts. So what will happen? By the addition of sulfoxonium we will get this product. Why this is happening in below the plane? Because there is an adjacent methyl group just above the plane. So it will give some steric effect. So that's why it will form below the plane because of this methyl group steric effect. Lots of things you have to see here, there is a happening in the new reagent you are getting, and this is steric effect. Because of this one, it is happening below the plane because of the steric effect of methyl. And next, the A, what will be the A? Because see, there is a OH group. There is a OH group. That's why it is above the plane. That means it's coordinating. So what type of reagent can be possible? It will be by this type of uh, Simon-Smith reaction. So A will be Simon-Smith because we have already this is to coordinate with the OH bond to give this type of selective compound. So this is the mechanism. So this I will remove this. So this is our product. So for this one, we have to use Simon-Smith reaction, and by due to coordination, we will get the above product selectively. And for the rest reagent also, I have shown the product. When we are adding sulfoxoniamide, we will get this product. And what sulfoniamide does? I have told about this sulfoniamide. What sulfoniamide does? Sulfoniamide does what? The sulfoniamide, if there is any carbonyl group, it will react with this, giving a epoxide. Sulfoniamide, what does? It gives epoxide. So if we choose, so you have to be careful by choosing the options also. Like what you see, this difference is about the oxygen. So if we are giving sulfoniamide, we would get this this one. So that's why it can't. So the option, what will be the option? So this one is B, and this one is so. No, sorry. I think I have. So what will be the correct option? I think this one. This is the correct option. This is the correct option. So this is the last problem of today's session. We have come to the end. The correct reagent for the affecting the following reactions are. So here see, it's complicated. Three types of from a single substrate, three types of product has been shown. For different substrate, you need different reagent to get. So see, there is a carbonyl group is there. There is a alpha beta unsaturated double bond is there, and there is a electron rich double bond is here. There are three types of unsaturation. There are showing different pane. There is three type of unsaturation. So what I have just taught, what when this type of electron rich double bond gets cyclopropanation, what type of reagent to use? Simon-Smith reagent. When this type of alpha beta unsaturated double bond gets cyclopropanation, what type of reagent do you use? That sulfoxoniamide. And when the epoxide gets cyclopropanation, sorry, the carbonyl gets react and giving us the epoxide, what type of reagent do you use? Sulfoniamide. So from the option we can choose that here that is alpha beta unsaturated. So what is the page? So this one is alpha beta unsaturated, so it will be sulfoxonium. So from this, so already these two options are cut. These two options are cut. So we will go from between this and this. So B is sulfoniamide epoxide, sulfoniamide. So both are the same. So what will be the C? Where this double bond is getting reacted, this electron rich double bond. Well, this is will be simple Siemens-Smith reaction. The Stabile reagent I haven't taught, I haven't discussed yet. If you guys interested, I can discuss that in the next session also. What is Stabile reagent? So that, so for now I just know that tab reagent can't do this reaction. So what will be the reagent? This is a Simmons-Smith reaction. So what is our product then? So this is the correct option. So here I have shown all the that was a Korey-Chaykovsky. So Korey-Chaykovsky. So for the first one, on the sulfoniumide, it will give this epoxide. For sulfoxoniumide, it will give the alpha beta unsaturated cyclopropanation. And for the Simmons-Smith reaction, we will get cyclopropanation of this electron rich double bond. So, for enough, so this is enough for today. So that's it for today. We'll meet in the next session, and I will discuss some more problems based on this carbene reactive intermediates, carbene and nitrene also when it will be taught. And and if I have I have given two tasks to you guys. So if you get some time also or interest, you can try to think about those tasks, and I will solve those problems next week definitely. So you will get your answers. And meanwhile, on 8th maybe you will get you have to submit your assignments also. You will get the answer key. Regarding that also, if you have any queries like why that answer is happening or why that answer is happening, you can upload that in the feedback form. I will come to know that if there is any issue regarding the answer key also, like if you have any doubts, I will be there to clear that, and I will come next week with some more problems. So thank you for. So I will upload the video link. Maybe NPTEL, I will send the link to the NPTEL. They will upload the link, and I will upload this. If it's possible, I will upload the slides also so that you can get the questions easily. And let's meet next week. I hope you guys enjoyed my session. This was my first session, so I think you guys have enjoyed, or this is a great opportunity for me to learn more about to teach you, and it will also help me to interact with you guys. So if you guys have any issues or any doubts or anything, you can upload that in feedback form or in the comment box also. I will try to resolve all these things, and whenever and if any issues is there for the next session, you can ask all those things also directly in the comment box. I will try to solve that one. Thank you everyone. So goodbye.